Welcome to class. In today's class, we are going to be briefly looking at redox reactions. In the last video, I talked about redox, that is a reaction involving oxidation and reduction. Oxidation and reduction involves two opposing yet complementary processes. Redox reaction involves two opposing yet complementary processes. And those two opposing and complementary processes, one is oxidation, the other is reduction. Every oxidation must be accompanied by reduction and vice versa. Vice versa means that every reduction must be accompanied by oxidation. Each of those reactions cannot exist by itself independently. The reason is because if we say that oxidation is a process of losing electrons, oxidation cannot exist by itself because a substance cannot donate electrons or lose electrons if there is no substance somewhere to accept that electrons are being lost. So, we are saying that for a substance to lose electrons, there must be another substance to accept that electron. If oxidation is the process of losing electrons, then there must be another process which is a gain of electrons, and that other process is reduction. So you can see how complementary those processes are. Let's begin. If you look at this reaction, this is a reaction between potassium iodide, aqueous. This is ion 3 tetraoxosulfate 6 producing iodine gas and potassium tetraoxosulfate 6 and ion 2 tetraoxosulfate 6. Remember, what we have here is ion 3 tetraoxosulfate 6 and what we have here is ion 2 tetraoxosulfate 6. If you look at the physical states, aqueous, alright, this is gas. Why is this? What do we mean by saying that a substance has a physical state that is aqueous? A physical state that is aqueous simply means that the solvent for this substance is water. The solvent by which potassium iodide is mixed with is water. The solvent here is water. The solvent is water, the solvent is water. That's what aqueous means. Considering this reaction, how does a substance lose electrons? How does it gain electrons? Because I want us to represent the oxidation half equation and the reduction half equation. Because these two reactions complement each other, each of the equations is very valid to bring about an overall reaction. Just before that, we investigate this. If you look at your potassium iodide, it is dissolved in water. It simply means that the ionic representation of this substance is represented that potassium iodide, these substances, because potassium is not in ground state and iodine is not in ground state, that means potassium loses or gains electrons, iodine loses or gains electrons. The representation, the value representation is this. Potassium will not gain electron, it's going to lose electron. That's why you're seeing a positive charge here. Iodine is not going to lose electrons, it's going to gain electron. That's why I'm seeing a negative charge here. Remember my last video? And what I am putting below here, this is Arrhenius theory. We are going to talk about Arrhenius theory when we're looking at electrolytic cell. So just stay tuned for more videos. But what you're seeing here is Arrhenius theory, alright? But what you're seeing here is a modified, a modern form of Arrhenius theory. That potassium iodide contains positive ions and negative ions. Because it is not in ground state, it is losing electron, potassium, to iodine, and iodine is getting electrons from potassium. It is important to understand that in the aqueous state or form of this substance, we have these two ions inside, which can also be represented as this. And it's also important to understand that in this other substance, this is ion 3 tetraoxide 6. We have this potassium ion, this iodide ions. We have ion 3 ions, all right, and then we have tetraoxide 6 ions. There's a little error there. We don't need to put this. Yes, we don't need to put this. This will be included when the valency of this comes here, all right, and the valency of this comes here. So that's not necessary. That's not necessary. Yes, and if you also look at this, this will not be necessary, all right, because according to the rule, this will cancel, the charges will cancel, the valencies cancels, all right. So ignoring the negative sign, 1 comes here and 1 comes here. So this is it, all right. Let's correct that. So the substance I'm representing here is the substance you're seeing here, all right. So back to the substance. So for this ion, for this substance, it contains ion 3 ions. Ion 3 ions, I'm talking about, I'm saying that this ion has lost 3 electrons. That's why it's going positively charged. And this tetraoxide 6 ion. This is a polyatomic ion. We will look more about that. You can call it a radical. We'll talk more about this in subsequent videos. And this product is ion 2 tetraoxide 6 aqueous solution. It contains ion 2 ions and tetraoxide 6 ions. Moving forward from there, since we know this, potassium iodide produces iodine. If you look at what is happening there, you would agree with me that these iodide ions, all right, which is I minus, meanwhile, it will be necessary to balance the chemical equation at once. Let me balance the chemical equation at once. I think it's balanced right now. Okay, you can check out my video on balancing chemical equations, and that will be very correct. So the iodine ions in this substance, all right, produces this. If you look at this, it means that this atom has gained 1 electron. If you look at this substance, I am not seeing any charge here. That means this is at ground state. That means the charge is what? 0. The charge here is minus 1. The charge here is 0. Note this. If we say that oxidation is a process of losing electrons, when electrons are lost, the charge of an atom increases. That's the overall charge. And when electrons are gained, the charge of an atom, the overall charge of an atom decreases. If you look at this substance, the charge here is minus 1. Of course, it means the oxidation number is minus 1. We will talk about oxidation numbers as we proceed. Just stating. And if you look at this substance, the charge here is 0. That means the oxidation number is 0. The charge here is minus 1. Oxidation number is minus 1. And this is 0. What happened? If you look at what is happening here, you will see that there is an increase in charge from minus 1 to 0. Okay. In that increase, you would agree with me that this substance did what? Lost electrons. This substance lost electrons. How can I represent this? This can be represented formally as I minus E give me I2. So it lost one electron, alright, and the charge is what? 0. But if you look at this critically, we have balanced the charges. -1, -1. Yes. -1, -1. Minus is plus. So that's -1 plus 1. That's how I got the 0. Yes, of course. The charge is 0. So the left hand side, the charges are balanced. We are balanced the right hand side. But the problem we have is that we have 2 atoms of iodine, ground state here. We need to apply these 2 over here. So to balance the atoms, we balance the charges. To balance the atoms, we would say that this will be 2. Alright. We put 2 here. That 2 would affect here. So we have balanced the charges. Because of these 2 atoms of iodine, we need to balance this. And of course balance this electron. So at the end of the day, 2 times -1 is -2. Minus, see that minus here? 2 times each electron is -1. That's the charge. That will be -2. So -2 minus into -2, -2 plus -2, that gives me 0. So this is it. This is the oxidation half equation because this loses 2 electrons. That's 2e minus. A more proper representation of this is that we take -2e to the other side. So we now have our oxidation half equation. Let's look at the reduction half equation. If we look at this substance, like we have here, contains F3 plus SO2 minus. So in this substance, alright, you would see that the ion 3 ions in this substance, which is Fe3 plus, the next place we saw an ion was in ion 2 6, will give us Fe2 plus. Having 3 plus became 2 plus. If you notice what's happening here, the oxidation number here is +3 and the oxidation number here is +2. Have you noticed that there is a decrease in oxidation number? Whenever there is a decrease in oxidation number on the charge, know that there is a what? There is reduction. And what is reduction? Gain of electrons. That means this substance gain electron. That means this substance gain electron. And what gained electron in that substance was ion 3 ions, gained electrons and became what? Ion 2 ions in ion 2 6. Yes. Yes. This is ion 2 6. This is ion 3 6. So that means this atom, because how many electrons did it gain? The oxidation number dropped by 1, like +3 to +2. That means it gained 1 electron. So I'll put here E minus 3 plus. Alright. Now I need to balance this. I need to balance this. So how am I going to balance it? Or is it balanced? So 3 plus this. I think that's balanced. But if you notice something happened there. Very interesting thing happened there, which I really want you to pay attention to. To balance the charges, this is a gain of electron. Here we said minus because it lost electrons. Here we are putting plus because it gained electrons. Yes, he gained electrons. Now, if you look at this, you discover something that this was two atoms of iron. That's two atoms here. Alright? And in the product, we are having just one atom. So, to balance this, we are going to do something very interesting. We will just add 2 here. The reason is not even because of that. The reason is because if you look at the oxidation equation, the oxidation equation exists because there is a reduction equation. The electrons here in this equation is 2 electrons. So we balance the electrons. I have 1 electron here, 1 mole of electron here, and then I'm having 2 moles of electron here. What will I do? What will I do to make the moles of electron here and the moles of electron here to be the same? The coefficient of the electron here is what? 1. So that means I will multiply everything here. I will multiply everything here by 1. And it will still be the same thing. That's 2i minus, give me i2 plus 2e minus. And then I will multiply everything here by the coefficient of the number of moles of electron here. So the number of moles of electron here is 2 times 2. 2 plus times 2. Yes. So when I do that, the 2 will apply here. So this will be 2Fe3 plus 2E minus, give me 2Fe2 plus. So it is because of the number of moles of electrons in the oxidation equation that I used to multiply the reduction equation. So I can call this reduction half equation. Reduction equation. So you can see what is happening there. You need to reduce the oxidation half first, balance the charges, and then the reduction half. You use the charges, the number of moles of electrons in the oxidation half, to know how you're going to balance the number of moles of electrons in the reduction half equation. Yes. You know that if this was 3, alright, I will multiply this by 3, and then I will multiply this by 2. You know. Let's proceed. So, we have gone ahead of ourselves, we have balanced this. Now, what if I am to put the 2 equations together? Let's put the 2 equations together. The oxidation and the reduction half equation. Let's put it together. If we put it together, okay. E3 plus. Okay, let's put it together. We're going to have Fe rather. We're going to have 2i minus. Let me break it down a little bit. 2i minus, alright, plus 2Fe3 plus 2e minus. This is the right hand side, this is the right hand side. Alright, the left hand side, I would have 2Fe2 plus I2, alright, plus 2e minus. 2e minus, you can put 2e minus. Or you take 2e minus to the other side. It will become plus minus 2 minus 2e minus. That's minus 2 minus minus 2. This thing means minus 2. 2 times minus 1 minus 2. Alright, this minus 2 plus 2, that is what? 0. So that's why I say that this will cancel. If you take this to the other side, it will cancel. It will be 2e minus minus 2e minus. That gives me 0. So my overall redox equation is plus Fe3 plus, giving me 2Fe2 plus I2. Yes. Some persons may decide to write it like this. You know, they want to put the metallic ion first. So Fe3 plus, alright, plus 2i minus, giving me 2Fe2 plus I2. This is my overall redox reaction. This is correct, this is correct. Anyhow you want to write it, they mean the same thing. We proceed. Before we wrap up this class, let's go back to the normal chemical equation. Before we began to look at the ionic representations of the ions present in the atoms of the substances that reacted to give us this product. If you look at this substance, you will see that the iodine in potassium iodide did what? It lost electron and then produced iodine ground state. This process of losing electron, this process is oxidation. Oxidation. And the substance that loses electron, the substance that undergoes oxidation is called the reducing agent. Reducing agent. You can just use Ra to represent that. And this substance, which contained ion 3 ions, and ion 3 ions became ion 2 ions, and the ion 2 ions was found in ion 2 tetraoxide 6. You can see that that process is the process whereby ion 3 ion gain electron and then undergo reduction. That's a reduction process. It's from here that we have the reduction half equation. And you can also see that if this substance undergoes reduction, that means that this is the what? This is the oxidizing agent. Oxidizing agent, I'm just using OA. Oxidizing agent. So, we have been able to investigate the redox reaction between potassium iodide and ion 3 tetraoxide 6 to give iodine gas, potassium tetraoxide 6 and ion 2 tetraoxide 6. Potassium is not losing any electron, the oxidation number is +1. The oxidation number of potassium is +1. So potassium did not lose, there was no difference in the electron, it's still +1. The oxidation number is still +1. Alright, so we come to the end of this class. Don't forget to share. We come to the end of this class. Alright, I believe you learned so much from what we have done. Please share, click the notification bell so that others will get to have these videos. We are going very deep because in our next class, we'll be looking at how we can calculate oxidation numbers. Stay tuned, let me master, share. Thank you so much.